So up until this point, everything was binary. It is trivial to generalize decision trees to multi-class classification problems. So the main difference is now instead of just the positives and the negatives, you have k different classes. But these k classes, the instances with those classes, they'll get sorted into the leaves of the tree in the same way that binary classes did. So the only difference is how you define the entropy. Remember, the entropy previously, it was p plus log p plus p minus log p minus, and then take the negative value of the whole thing. Now you just generalize it, right? You have p of c, which is the proportion of the subset which is labeled with class c. So you take pc log pc, and then you add it up over all possible classes. Previously, we just had two classes. Now we're going to have k classes, but the definition is the same. So the entropy is pretty much the same, the information gain the same, the algorithm proceeds in exactly the same way, and once you're at the leaf, if the leaf is not pure, if you have pruned the tree or stopped growing it early, then the decision is based on the most frequent class in that leaf. So if a leaf node has 2 examples of brown eyes and 3 examples of blue eyes and 1 example of black eyes, then you would pick blue eyes as the predicted class, if you were trying to predict eye color for some reason. So that's multi-class. You could also use decision trees for regression. It is a little bit more complicated. So regression, remember, instead of predicting a class, you're predicting a real number, such as, you know, the stock price of a company tomorrow. That would be a regression task. So you're trying to predict numbers, so you don't have classes anymore. This makes 2 things difficult. 1, how do you do prediction once you've sorted the data? And 2, how do you define entropy now that you don't have classes? Remember, so entropy usually looks like that. You're summing up over a discrete set of classes. And now instead of a small set of classes, you have the real numbers as the possible outputs. And you can't really compute p for every real number anymore, because any given subset, it'll have some numbers, but it won't have other numbers in it. So you can't use entropy. So in practice, what's done, if you're following the book, it's section 6.5. Instead of using entropy, instead of trying to maximize the gain, what you do is you try to find subsets such that each subset has the smallest variance of whatever it is you're trying to predict in that subset, right? So if you're predicting the stock price of something, then you try to split the data in such a way that in one subset you will have all the days on which some stock traded very, very low, and then in another subset you would have values where it had sort of middling and then high. So you try to split into subsets based on the variance. And then once you have sorted the data into subsets, the decision is similar. What you do is you travel down to the leaf node. At the leaf node, you have a bunch of instances. Each instance has a label, a real number, and you take those real numbers and you average them. And you output that average as the prediction from the decision tree. There is a variant that's described in the book where instead of just taking a simple average, you actually fit a small linear model to that. And that will make a lot of sense when in a few lectures Nigel talks about linear methods and how you use those for regression. Basically, you would be fitting lots of different linear models at the leaves of the tree instead of one big overall linear model to the entire data set.